Geometry, Chapter 3, Circles, Module 10. In this module, we'll solve sums on problem set 3. Question number 7. In the adjoining figure, circle with center x and y touch each other at point Z. A secant passing through Z intersects the circle at point A and B respectively. Prove that radius XA is parallel to radius YB. In your textbook, this question is in the form of fill in the blanks and you have to complete the proof. In this particular video, I will be doing the entire proof. So it is given x and y are the centers of the circle and we have to prove radius XA is parallel to radius YB. Construction. So we'll draw segment XZ and YZ. If you see this dotted line in the figure is a construction. So we join XZ and we join YZ. Let us start with the proof. By theorem of touching circles, we know that here point X, Z and Y are collinear. And therefore angle XZA will be congruent to angle BZY as they are vertically opposite to each other, and we know that vertically opposite angles are congruent. So we'll just assume that angle XZA and angle BZY will be A, some angle A which is unknown. So therefore angle XZA equal to angle BZY is equal to A, and we'll call that as equation 1. Now, segment XA, if you look in the figure, segment XA will be congruent to segment XZ as they are the radius of the same circle. And angle XAZ will be equal to angle XZA. That is, angles opposite to equal sides will be equal, or angles opposite to congruent sides will be congruent. So since side XA is congruent to XZ, their angles will also be congruent to each other. And we have said that angle XZA is A. So angle XAZ will also be A as they are congruent to each other. Or we can also say by isosceles triangle theorem. We'll call this as equation 2. Similarly, for the bigger circle, segment YB will be congruent to segment YZ as the radius of the same circle, and angle BZY will be equal to angle ZBY. We can say by the same theorem that angles opposite to congruent side will be congruent, or simply we can say by isosceles triangle theorem. And since we know that angle BZY is A from equation 1, angle ZBY will also be A. We'll call this as equation 3. Now from equation 1, 2 and 3, we can conclude that angle XAZ, if we see in the diagram, this one, angle XAZ will be equal to angle ZBY. That is this angle from 1, 2 and 3. So since they are forming a pair of alternate angles and AB will be the transversal, XA should be parallel to BY by the alternate angle test. So we can now say that radius XA is parallel to radius YB. Question number 8. In the adjoining figure, circle with center X and Y touch internally at point Z. Segment BZ is a chord of a bigger circle and it intersects smaller circle at point A. We have to prove that segment AX is parallel to segment BY. Let's start with the solution. It is given X and Y are the centers of the circle. We have to prove AX is parallel to BY. Let us start with the proof. If you see in triangle XAZ, segment XA will be congruent to segment XZ. as they will be the radius of the same circle. And segment angle XZA will be congruent to angle XAZ. This we can say by the isosceles triangle theorem, or we can also say that angles opposite to congruent sides will be congruent. So the congruent sides were XA and XZ, and the angles opposite to them were angle XZA and angle XAZ. Hence they will be congruent to each other. Also, if you see in triangle YBZ, by the similar conditions, we can say that segment YB and segment YZ will be congruent to each other, as they will be the radius of the same circle. And we can also say that angle YBZ will be congruent to angle YZB. Same by isosceles triangle theorem, or we can also say that angles opposite to congruent sides are congruent. These two sides were congruent to each other, that is side YB and YZ, and the angles that were opposite to them were YZB and YBZ, so they'll be congruent. Or you can simply say by isosceles triangle theorem. Also, angle XZA will be congruent to angle YBZ. As you can see, YXZ. Therefore, angle XZA will be congruent to angle YBZ. So from equation 1 and from equation 2, we can say that angle XAZ will be congruent to angle YBZ. And by the corresponding angle test, we can say that segment AX will be parallel to segment BY. Question number 9. In the adjoining figure, line L touches a circle with center O at point P. Q is a midpoint of the radius QP. RS is a chord through Q such that chord RS is parallel to line L. RS is 12. We have to find the radius of the circle. Let us start with the solution. Let the radius of the circle be R. And line L is a tangent to the circle which is given to us in the question. Segment OP is the radius. So OP is the radius of the circle. We can see that in the diagram as well. And since L is a tangent, and we know by tangent theorem that the radius is perpendicular to the tangent, so segment OP will be perpendicular to line L, as segment OP is a radius by tangent theorem. Chord RS is parallel to line L. This is given to us in the question. So segment OP will be perpendicular to chord RS as well, because RS is parallel to L and OP is perpendicular to the tangent L. So OP has to be perpendicular to the chord RS also. Perpendicular, the reason for that we can say is perpendicular drawn from the center of the circle to the chords, it bisects the chord, and since the perpendicular OP will bisect the chord RS, so it will bisect, that the meaning of that is RQ and QS will be equal, or in other words we can say that QS will be half of RS. And we know RS is 12 is given in this question, so we just substitute it. So half into 12, so we can just reduce this and we'll get 6 centimeters. So QS is 6 centimeters. Also, OQ will be half of OP, as Q is the midpoint of OP. So since Q is the midpoint of OP, OQ will be half of OP. And we know OP is the radius of the circle, which is R. We considered radius of the circle to be R at the beginning of this question. So in place of OP, I'll just substitute it R. So this becomes half into R. Now, in triangle OQS, we know that angle OQS will be 90 degrees because it is perpendicular, a segment OP is perpendicular to chord RS. And since it is a 90-degree, a right angle triangle, we can use Pythagoras theorem. OS will become the hypotenuse. So therefore, OS square is equal to OQ square plus OS square by Pythagoras theorem. And we know that OS is the radius of the circle, and we consider the radius of the circle to be R. So in place of OS, I just substitute R. So this becomes R square. OQ, we found out in a previous part, it is half into R. So this becomes half into R the whole square. Plus OS is 6, we found out in a previous part of the question. So we substitute this and it becomes 6 square. We'll just simplify this part now. So this becomes R square, and half, the square of half will be 1 by 4, that's 1/4 into R square, plus square of 6 is 36. So we'll take this 1/4 R square on the other side. So it becomes R square minus 1/4 R square. We'll do cross multiplying and we'll simplify this portion here. So we get 3/4 R square equal to 36. So we take this 4 on this side, it will get multiplied. And if we rearrange this, we get 36 into 4 divided by 3. So if we simplify this, we get it to be 48. So R square is equal to 48. And if we take the root on both the sides, so we get R is equal to square root of 48. And square root of 48 is 4√3. So the radius of the given circle is 4√3 centimeters. 10th sum. In the adjoining figure, segment AB is a diameter of a circle with center C. Line PQ is a tangent which touches the circle at point T. Segment AP is perpendicular to line PQ and segment BQ is perpendicular to line PQ. We have to prove segment CP is congruent to segment CQ. Let's start with the solution. It is given that C is the center of the circle and AB is the diameter of the circle. Line PQ is a tangent and segment AP is perpendicular to PQ, and also segment BQ is perpendicular to BQ, the tangent PQ. We have to prove segment CP is congruent to segment CQ. So for that we need to do certain constructions. We will draw segment CT, segment CP and segment CQ. So if you see in the diagram, we've just drawn segment CT, CP and CQ. Is a tangent to the circle at point T. This is given in the question. Therefore, segment CT will be perpendicular to line PQ. This is by the tangent theorem. Also, AP will be perpendicular to line PQ and BQ will be perpendicular to line PQ. That is given to us. Therefore, we'll have segment AP will be parallel to segment CT, which indeed will be parallel to segment BQ. So we'll have these three lines which are parallel to each other. Hence, we can say that lines perpendicular to the same lines are parallel. By this reason, we can say that AP, CT and BQ are all parallel. Therefore, we can say AC upon CB will be equal to PT upon TQ. This is by property of intercepts made by three parallel lines and they are transversals. Or in other words, we can say it is a basic proportionality theorem. But we know that now AC is equal to CB as they are the radius of the same circle. So in this proportion, in place of CB, I will substitute AC. So we'll get AC upon AC is equal to PT upon TQ. Now AC upon AC will become 1. So we'll get PT upon TQ equal to 1. And hence we can cross multiply. We can take TQ on the other side and it will be PT is equal to TQ. We'll call this as equation 2. Now, you see in triangle CTP and in triangle CTQ, segment PT will be congruent to segment QT by equation 2. We just proved it. PT congruent to QT. And angle CTP will be congruent to angle CTQ because both of them are 90-degree angle. And segment CT will be congruent to segment CT itself because it is the common side in both the triangle. So we can say that the two triangles, that's triangle CTP is congruent to triangle CTQ by SAS test of congruency because we have proved two sides and one angle to be congruent. Therefore, since we have proved that the two triangles are congruent, we can say that segment CP will be congruent to segment CQ by corresponding sides of congruent triangles. Question number 11. We have to draw circles with center A, B and C, each of radius 3 centimeters, such that each circle touches the other two circles. So this we just analyze on how to draw such circles. So let the circle with center A, B and C touch each other at point P, Q and R. So we know A, P and B will be in a straight line. That's point A, P and B will be collinear. Point A, Q and C will be collinear. And point B, R and C will be collinear. So we can use theorem of touching circles. And we can say that AB will be equal to AP plus BP as AP and B are collinear. And AP and PB are 3 centimeters, so we'll just substitute it. So AB will be 3 plus 3, which is 6 centimeters. Similarly, we can say that BC and AC will be 6 centimeters. So if we construct triangle ABC of side 6 centimeters each, then with A, B and C as the center with radius 3 centimeters, the touching circles can be drawn. Question number 12, we have to prove that any 3 points on a circle cannot be collinear. So let us write what is given. A circle with center O, point A, B and C lie on the circle, and we have to prove point A, B and C are not collinear. Let us start with the proof. In the circle, if you see OA equal to OB, as they are the radius of the same circle. Therefore, point O is equidistant from the end point A and B of segment AB. Point O lies on the perpendicular bisector of AB. By perpendicular bisector theorem, so similarly we can prove that point O lies on the perpendicular bisector of BC and point O is a point of intersection of perpendicular bisector of AB and BC. That is, it will be the circumcenter of triangle ABC. We'll name that as equation 1. Now suppose that points A, B and C are collinear. Suppose if they are collinear, then the perpendicular bisector of AB and BC will be parallel. Perpendicular, that is, they have to be perpendicular to the same, perpendiculars to same lines are parallel to each other. Therefore, the line perpendicular bisector do not intersect at O. This contradicts to statement 1 that the perpendicular bisector intersects at O. So we get a contradiction, and from here we can say that our assumption that ABC are collinear is wrong. So we can state that ABC is points A, B, and C are not collinear. Thank you.